Now we know the positions of the maxima and minima, but the light intensity is a smooth function that varies continuously with your position along the screen. We want to find the equation for the intensity of the light at any point in the interference pattern. The thing we start with is that the electric field of each wave can be shown as a sine function, as we've seen before. The two waves have the same amplitude, that we'll call E0, and the same angular frequency, omega. Then the total magnitude of the electric field at any point on the screen is the superposition of the two waves, which means that we just add the functions together. We will write the equation for each wave as shown. R1 will have the equation that E1 equals E0 sine omega t, and R2, the longer ray, will lag behind it slightly by the time it reaches P, with E2 equals E0 sine omega t plus phi. And phi here will be the phase difference between the two by the time they've reached the point P. So the phase difference depends on the path length difference between the two. We already have the expression for the path length difference between R1 and R2, and that, which is delta L, equals d sine theta. Now, if the path length difference is a whole wavelength, that corresponds to a phase difference of 2 pi radians, which is one complete wave. If the path length difference delta L is some fraction of a wavelength, then the phase difference phi will be the same fraction of 2 pi. We have phi over 2 pi equals delta L over lambda, so phi over 2 pi equals d sine theta over lambda, and when we rearrange that, we get the expression at the bottom. Phi is 2 pi over lambda times the path length difference, which is 2 pi over lambda times d sine theta. Then, by the principle of linear superposition, we just add up E1 and E2. We use a trigonometric identity that you probably did at school and then forgot to get the resultant wave as another sine function where the amplitude is multiplied by 2 and by the constant factor cos phi over 2. So we have the electric field at P is 2E0 cos phi over 2, and all of that is a constant, times sine omega t plus phi over 2. So the expression for the intensity comes from the fact that the intensity of a wave is proportional to the electric field squared. So we end up with the equation I equals I max cos squared pi d sine theta over lambda. And since we're making our assumptions that theta is very, very small, in other words, the distance to the screen is much larger than the slit spacing, we can approximate that as I equals I max cos squared pi d over lambda L times y, where y is the distance from the centre to the point that we're interested in. So this is just the form of the equation because we haven't yet found out what the maximum intensity can be. But you can see at the bottom right there a graph of a cos squared function. So we remember that the cos function is the one that's a maximum 1 at theta equals 0. And so the cos function is the one in the dark purple, going up and down from +1 to -1. Then cos squared is a little bit narrower. It is only positive. And so it is 1 whenever the cos function was 1 or -1. And so it has a peak in the middle, and then it has equally spaced peaks. The final equation for the intensity of the light is shown. We see that I is 4I0 cos squared a half phi, and phi, we remember, is 2 pi over lambda times d sine theta. So the amplitude of the resultant is actually 4 times the amplitude of the light from one of the slits on its own. Remember, the intensity is E squared, and so we have double the amplitude of the electric field. That makes 4 times the intensity. That is only true with our assumption that the two light sources are coherent, so that there is a steady pattern. If the two sources were incoherent, which means no fixed phase relationship between them, there would be no fringe pattern, and the intensity would have the uniform value 2I0, as shown by the dotted line on the graph. So light from two independent sources, like lasers of two different wavelengths, or even light of two different polarizations, will not produce an interference pattern.